Hello, my name is Gary Millett, and I'm going to talk to you today about topic number 5 in the course ELE 110, Electronics for Technicians 1, and that topic is Basic Electrical Circuit Theory and Ohm's Law. So this slide shows a graphic of a voltmeter and ammeter that are connected to a circuit. The voltmeter is across the battery on the left-hand side of each circuit, and the current meter is in the circuit between the battery and the resistor. So you see part A here, less voltage, less current. Part B, more voltage, more current. So that's the effect on the current of changing the voltage with the resistance at a constant value. So years ago, a fellow named Ohm experimentally determined that doubling the voltage applied would double the current in the circuit. And of course, this is known as a linear relationship. So Ohm's law, as it's understood today, provides a relationship between current, voltage, and resistance. This figure shows the effect on the current of changing the resistance with the voltage at a constant. So notice the battery now doesn't have an arrow through it, which would represent in the prior slide a variable voltage. So the voltage meters in both A and B here are exactly the same, but the resistor in part or figure A is 10 ohms, whereas the resistor in figure B on the right-hand side is 20 ohms, or double. And what you notice is if you were to count the little red lines on the current meter on the figure A, you'd see a certain number, and there's half that number on figure B. That is, increasing the resistance has halved the amount of current. That's an inverse relationship. So these are the three variations of Ohm's law. I'll just list them right now. I equals V over R, V equals I times R, and R is equal to V divided by I. So those are all just rearranging the symbols in the algebraic equations there. So let's go back to the first one. What's the current? I is equal to the voltage divided by resistance. So if the voltage V and resistance R are known, then one may calculate the current I. That's one way we could use Ohm's law's equation. The next one, V equals I times R. If the current I and the resistance R are known, then one may calculate the voltage V. So if you have a resistor and you know a current is flowing through the resistor, you can calculate the voltage across the resistor, what we commonly call the voltage drop across the resistor. And the last equation says that R equals V over I. So if the voltage and the current are known, then one may calculate the resistance R. So you might be told what the voltage is across a resistor and the current through it. This would allow you to calculate the resistance R. Again, these are three equations which are tools that you might use to take and determine circuit values. So Ohm's law can be manipulated in three different ways here. This graph, or this slide, shows graphing current versus voltage. So it shows the figures A, B, and C here, and the figure on the A shows a battery that goes from 10 to 100 volts. It's a current meter that's in the circuit and a 10 ohm resistor. So if we just use Ohm's law real fast, if we have voltage at 10 and resistance at 10 ohms, we divide 10 by 10 and we'll get 1 amp. Part B shows a graph of this relationship with the voltages every 10 volts, so it goes from 10 to 100, and notice that you see 1 amp up to 10 amps. If that was a 10k ohm resistor, we'd have 1 milliamp up to 10 milliamps. The graph on the right-hand side shows the points of the chart there, shown on the graph and plotted, if you will. And it turns out that the slope of the red line is the resistance, because actually the slope of the red line is equal to, if we go back to the prior slide, R equals V times I. So this graph depicts a linear relationship. If I have a doubling of the voltage, I have a doubling of the current. So this is a little historical note on Greg Simon Ohm, who lived back in 1787 to 1854. Basically, he's a physicist, and again, he studied these basic electrical properties, and he used wire basically for his resistors. So that brings us to the concept of energy. What is energy? Energy is the ability to do work. There are many different types of energy. I think I have a presentation that I'll post in another week about this. Energy may be transformed from one type to another. And today we consider the various sources of energy to be of two types, renewable or non-renewable energy. And just as a side note here, we're presently in an era, it's October of 2022, and various political entities like the state of California have decreed there will be no more internal combustion engine cars. Everything will be either electric or maybe it's powered by hydrogen. So what that means is we're going to have to do a very fast electrification in the United States in the near term to be able to take and supply electricity to all of these cars. It only makes sense that the electricity is renewable, that is clean solar or wind farm energy, but it's going to be extremely difficult to get that much energy in a short period of time from renewables. It seems that the more logical way to do it, the more practical way is to use gas to produce electricity, because gas is the cleanest of the fossil fuels. So the physics concept of work is shown in the following slide. So in physics, the mechanical work, or mechanical work I should say, is defined as force times distance. So if I apply a force through a certain distance, I'll do a certain amount of work that's shown by the equation below. W equals F times D. A practical example of this is pushing a car on a flat road. The more further one pushes the car, the more work has been done. So to extend these concepts, what if we're trying to push the car up an incline? Well, we got to do more work. What if we are pushing the car and we come to a downhill section of the road? Well, we might be tempted to jump into the car and coast down the hill. That would be returning potential energy into kinetic energy. Units of work in the MKS system are not very familiar to us. It's measured in joules, which is 1 Newton of force through 1 meter of distance. And again, joules, we're much more comfortable with watts. So this is now the concept of power. A more familiar term to us is power. Power is defined as the rate of doing work or the rate at which energy is used. So power in this equation, energy or work divided by time, is equal to joules per second. And then joules per second is equal to watts. So power is given in watts. So this slide is called the kilowatt hour unit of energy. So when the electrical utility company charges you for your electric usage, it's on the basis of the amount of energy that you have used, not the power. Hence, you are billed for kilowatt hours. You multiply the number of kilowatts times the time used. And you look at your electric bill or your parents, and that's what you'll discover. Of course, on electric bills in Massachusetts, about half the cost of the electricity is generating it. The other half is delivering it. This slide has an equation that says power in an electric circuit. So it turns out that if we have an electric circuit, the current flows and there's voltage applied to cause that current to flow, there will be power used. And the equation is power equals volts times amps, or V times I. On the right-hand side, we have several variations of this. If power is equal, one is power is equal to I squared R. Another one, if we take and change I to V over R, we'll find that power is equal to V squared over R. So these equations are similar to Ohm's law, 3 different forms of them. Again, power equals V times I, power equals I squared R, or power equals V squared over R. One should use the equation appropriate to the situation. That is, what do you know? If you know voltage and current, you can figure out power. If all you know is current resistance, you can figure out power that way. Or if all you know is voltage and resistance, you can figure out power using V squared over R. So where does the power go? Well, this shows a figure 4.1 is just power in an electric circuit is seen as heat given off by the resistance. So this is an academic circuit. There's a battery V on the left-hand side. a resistor R for the load, and heat produced by current through resistance is energy conversion. So electrical energy becomes heat energy. And that looks in this case to be energy that just simply escapes. So for these academic examples, the power supplied by the battery is wasted heat. In some cases, this is a technique used to heat people's homes or apartments with baseboard electric heat or portable space heaters. So this picture shows baseboard electric heaters. If you have one of these in Massachusetts, you're not very happy about it today because it turns out it's one of the most expensive ways to heat your house or apartment. These are more practical examples of what we call space heaters, and these things are a lot more practical than what I just showed in the prior slide because you can, put them into kind of a smaller space, a living area. There's no need to heat all the rooms in, say, a house or apartment. You can just use a space heater where people are gathered. Here's another one. There's an electric space heater, and you can see the elements are red hot or yellow, which means they are producing heat in that particular space heater. So this slide's called energy conversion and voltage drop in resistance. So what happens here is this figure 410 shows a battery on the left-hand side and shows a resistor R as the load. We know that the electrons flow from the minus side of the battery to the plus side of the battery. So what happens is as the current flows through the resistor R, the potential across resistor R would be plus to minus as shown, the plus on top and the minus on the bottom, the same as a battery on the left-hand side. And if I take and imagine myself walking around that circuit, let's say I start at the bottom and walk to the right, then go up through the resistor and have a voltage rise. If I go over to the left now and down through the battery, I'd have voltage fall, and the total voltage would be equal to 0 for that path. That is, the voltage applied is what the voltage is across the resistor. So electrons in this diagram lose energy as they pass the resistor, hence there's a voltage drop across the resistor. And again, note the polarity of the voltage. So we talk about a voltage drop across resistors when there is a voltage applied and a current flowing in the circuit. This is a picture 411 of a block diagram of a power supply and a load. In this case, we don't show a resistor, we just show a block, we call it the load, and we see the power supply has V out and there's a current flowing. In this case, the current is shown as conventional current flow, that is plus to minus, not what really happens in nature. So a common electronic system is a power supply. You'll find these in lab. Power supply, output voltage depending on the power supply circuitry. And most of these things are adjustable to give you whatever voltage you want. What about efficiency of electronic power supplies? Well, efficiency is equal to power out over power in. And of course, nothing's 100% efficient, so that would always be less than 100%. Power out is equal to power in minus power loss. What form does power loss take? Well, it takes wasted heat energy. And one last topic here, the efficiency of light sources. This diagram, a graphic shows the traditional incandescent light bulb that has been around for 100 years, a halogen incandescent, a compact fluorescent, or CFL, and a light emitting diode, or LED. And if you take a look here, the incandescent is rated as 100 watts. The halogen to produce the same amount of light would be 77. Compact fluorescent to give you the same amount of light is 23, and the light emitting diode is 20 watts. So it turns out they all produce 1600 lumens. The red in each diagram is wasted energy, and you notice how it goes down as you go from left to right there. So the other thing is that the price certainly is not, boy, if it's $45 a bulb today, that's pretty good for the LEDs. The prices have gone down dramatically for the LEDs. So most people have taken and changed over from incandescent as they burn out, or just done a wholesale changing of their light bulbs to save money. Joule is a little historical note about him. He lived 1818 to 1889, a British physicist. And the last guy is James Watt, who lived 1736 to 1819. He was a Scottish inventor and mechanical engineer. And they have both been honored by having things named after them. So that's it for this presentation.